a neurological condition that causes involuntary muscle contractions and hyperactive stretch reflexes. Any injury or diseases that affects the central nervous system, such as stroke, cerebral palsy, and multiple sclerosis, can cause spasticity.
Some of the tests for measuring spasticity are very subjective, not precise, and require a trained doctor to administer them properly. Our goal with our senior design project is to develop a spasticity monitoring device specifically tailored for our clients suffering from spasticity in order to determine the effectiveness of her medication and physical therapy.
This device must be self-administering, user-friendly, and portable so that our client can monitor her spasticity in the comfort of her own home. Also, it must be able to repeatedly provide quantitative measurements in order to track any changes in her spasticity over time.
Our solution incorporates the use of the pendulum test and the Android smartphone application. We will use the accelerometers in the phone to track her leg motion during the pendulum test and obtain specific parameters that will indicate changes in her spasticity over time.
Spasticity is clinically defined as a velocity-dependent increase in the stretch reflex amplitude. This means that if a doctor moves a patient's arm at a fast enough speed, the arm would resist and it would result in a catching motion. It is caused by a lack of inhibition from the central nervous system that results in excessive muscle contractions and hyperactive stretch reflexes. It is a result of many neurological conditions such as cerebral palsy, spinal cord injury, stroke, and sarcoidosis. In the United States alone, over 300,000 people are living with some kind of spinal cord injury, and more than 2/3 of them have been diagnosed with spasticity. Also, spasticity is found in approximately 1/3 of all stroke patients and 90% of multiple sclerosis patients.
Currently, the most common methods to measure spasticity are passive EMG recording, H-reflex test, Ashworth scale, and the pendulum test. Passive EMG recording involves placing electrodes on the leg and recording the signals using a computer. The problem with this is that it is not fully developed yet, and accuracy still remains to be an issue. The H-reflex test uses electrical stimulators on the nerve, and like passive EMG recording, the signals are recorded using a computer. This method is not dependable because the outcome depends on the placement of the electrodes. The Ashworth scale measures the resistance of the muscle to the movement caused by reflexes. This method is widely used, but it is very subjective and can result in inaccuracy. The last method is the pendulum test, which requires a patient to lift their leg and release it, thus resulting in a swinging pendulum motion. Afterwards, the angle of the leg is measured using an electrogoniometer. This is also a widely used method. However, it is bulky, expensive, and requires a trained physician.
Due to these shortcomings from the current solutions, we have several goals and specifications for our at-home spasticity monitoring device. The main requirement is for the device to be self-administrable so that our client do not need to depend on physical therapists. We also want our test to be reproducible for an accurate daily comparison. To minimize subjectivity, the device should have a quantitative output. The final device would be small, user-friendly, portable, and affordable.
We chose to create an Android smartphone application to track the motion of the client's leg during the pendulum test through the built-in accelerometer in the phone. After recording the data, we will extract it and save specific parameters such as the frequency, the amplitude, and the time constant so that she can track her spasticity levels over time. First, our client must locate a place to conduct the pendulum test. The location must have a stable object high enough for the client to sit on so that he or she can swing his or her leg freely during the test. After finding a suitable setup for testing, the device is strapped onto the leg. the start button is pushed. Then the client raises his or her leg. After the initializing sound is signaled, the leg is released, and the phone starts recording. After recording, the data can either be saved or the test can be repeated. The saved data can also be sent via email.
While the application was under development, a Wiimote was used as a prototype to record the pendulum test to administer a variety of tests and collect data. The Wiimote has a 3-axis accelerometer that records linear accelerations in the X, Y, and Z axes.
First, we had to make sure the accelerometer was sensitive enough to detect a difference in the pendulum test between a person with spasticity and people without. In order to do this, we compared the data obtained from our pendulum tests with our client's pendulum tests. From this comparison, we were able to determine that the accelerometer is able to detect the increased muscle resistance in a person with spasticity. Also, it shows that the amplitude and decay time constant can serve as good parameters to track our client's spasticity over time.
Since one of the shortcomings of the pendulum test is that it requires a trained physician to randomize the drop and determine the patient's spasticity, our first design concern was determining whether randomizing the drop was necessary. If it is necessary, then an external device will need to be designed to make the test self-administrable with a randomized drop. From these tests, we were able to determine that the knowledge of when the drop occurs does not affect the results of the pendulum test in either the control or the client.
We recorded our client's pendulum test constantly over the quarter while trying to keep the time and location consistent. From these tests, we were able to prove that the accelerometer is sensitive enough to detect a difference in degree of spasticity before and after receiving medication. As you can see on this graph, the purple curve represents her pendulum test after medication, which shows that her leg is swinging more freely.
So this is the main screen of our application, and it contains 5 buttons that the user can interact with. It contains a Start button, a Home, History, Facts, and Results button. Before we do a quick run-through of the application, I'll explain a little bit about how this application works. So here's a diagram or a picture showing the steps to use the application. And it's a very simple breakdown. So, the user press start, lifts their leg up, and drops when a loud beep is heard. So that is a simple breakdown of this application. And we'll go through it really quick right now. So all you do is press start. It's going to have 5 beeps to allow the user to get ready. And once you hear that loud beep, it starts. So now the accelerometer is actively recording the person's movement, and it will spit out data in the X, Y, and Z axes. And after about 8 seconds, the recording will automatically stop, and it will graph everything that it recorded. We can't show you here right now because of some limitations. It'll show an error, but generally it's going to look like this. It's going to have a graph with a bunch of data running all across. So next, it's also going to have history. So after saving the result, it's actually going to calculate the amplitude and the time constant of the resultant in the last saved result. And it's going to consistently graph the change in amplitude and time constant over a series of days. So that is our app, and I hope you enjoyed everything.